Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here, that represents our reactant side of our process. And then of course we have our empty container over here that represents our product side of the process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast, and at first a lot of water was switching sides going to the product side, but then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here. I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which is showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay, so if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Okay, now it doesn't mean that we have to have equal amounts. If we look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that, and that's not necessarily true. If we reset our setup here and we begin again, but this time instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay. Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference. Okay, so I am now at equilibrium. Okay, so switching again, I can do this all day long, and from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. Okay, I can just keep right on doing it and nothing changes here. Again, we have 140 plus. This particular scoop happens to be actually less in terms of what we have. Okay, it's not perfect with using scooping water, but again, we see 150 to 140, same amount of volume crossing over equilibrium. Okay, now in this case, if we look, we had equilibrium, so the process is at equilibrium. But if we look on the product side, we have much more water than we do on the reactant side. Okay, So in this case, because we end up with more product, we would call this a product favored equilibrium. We have less reactant, so it is not reactant favored. Okay? If you flipped it, and if you had a scenario where at the end you had something like this, this could be an equilibrium. It might mean you're using the big beaker for the product side and this little guy for the reactant side and scooping over and over again. If that was the case, if you have very little product and a lot of reactant left over, this is a reactant favored equilibrium. Still at equilibrium, still flatlined, but we have no change in reaction rate there. Okay, so if we go back to the idea of the graph in our notes again, we see the bottom graph shows the amount, and in that graph reactants were in red and products were in blue, I believe. So that was a product favored. So let's reset that to look like product favored, where once you've reached equilibrium, the rate of transfer, or how much gets transferred across, again our rate of transfer would be equal. So that would come together on the graph, but yet the amount of product would be more than the amount of reactant. At equilibrium, this would be product favored, which represents the second graph in that slide. Okay guys, that's the demonstration for this. We'll go back to our notes now. Thank you.